Math 1314, section IC1, spring 2022, Tyler Junior College. Section 3.3, complex numbers. Video 1, imaginary numbers and complex numbers. Disclaimer. The title of this section and the content of this section may make you wonder what on earth is going on here. Because some of the things you're going to see you may not have seen before. And when you see them, you'll start questioning why. So I want to beat it to the punch and let you know that what you're about to see on a theoretical level will allow us to finish solving certain types of problems which we haven't run into yet. They're next on the list of things to do. So that's reason number one, that, okay, this is to complete a task later. But if you start going, why, what's this stuff good for? When it was initially done, the answer was for completing another type of problem without having an application in mind. In fact, what you're about to see has existed for about 400 years, but really didn't have a useful application until as recently as about, I want to say 25 or 50 years ago. I can tell you that what you're about to see is responsible for things like wireless technology and cell phones. So you should be happy that somebody was nerdy enough to explore this concept just for the sake of exploring it. And then somebody down the road said, hey, we can use this to accomplish that. So I don't want you to get a little bit too freaked out as you start seeing some things right now that might violate the very tenets that you hold when it comes to math. For example, when you multiply a positive times a positive, it always comes out to be negative. Under the right conditions, yes, but that's about to change just a little bit. But don't worry, I'm going to lay out exactly what you need to know, how to pull it off, and everything's going to be fine. Trust me. In order to put imaginary and complex numbers in context and give you some sort of logical reason why they were existed / created / discovered, whatever your perspective is, I want to take you through a short trip on how math has been evolving for centuries. Now, what's under here are things that you already know, so don't panic. So I want to go back to the very first set of numbers that you probably know, which were called the counting numbers. The counting numbers are the numbers that you count with, 1, 2, 3, and 4. Okay, well, that's not bad. Everybody's been counting. Everybody knows how to count. It's not a big issue. Now, when you start throwing algebra in there, math with values that you don't know, I mean, you've been doing algebra since you've been seeing addition, subtraction, etc. You just didn't call it algebra back in elementary school, because if you called it algebra, it would scare the teacher. Probably wouldn't scare the student. It would just be another word. Like when you say square plus 2 equals 5, that's an algebra problem. You're just using a shape instead of a letter. And of course, you do what you do back in the day and you figure out that this is 3, so it's not a problem. Now, of course, if we wanted to make this look a little bit more like an algebra problem, I don't want to get rid of that, then you would put X instead of a box. So, but it's, I mean, you know how to solve this. Subtract 2 from both sides, go back to business and say X equals 3. Okay, so what's the problem? Well, this is a problem that we made up using an unknown and counting numbers, and the solution, X equals 3, is a counting number. So what could possibly be the problem? Well, here's what the problem is. The problem is we can't solve X plus 3 is equal to 3. Now, if you're thinking, yes, I can solve that. I know what its answer is. X plus 3 is equal to 3. Subtract 3 from both sides. Cancel these, and you get X equals what? If the only numbers you know are these, this has no solution. And you'd be surprised. I mean, we all know the solution is 0. That's not a problem. You'd be surprised the debate there was about the need for a digit that represents the absence of quantity. In other words, the number 0. But we know that 0 is kind of important, because if I give you back a paper and say, here's your grade, you're probably going to panic. And if I said, oops, I'm sorry, I left off a 0, but it was just a 0, I think you can see that, yeah, 0 is kind of important in our lives. So, okay, so we fixed that problem by coming up with the whole numbers, which is just the counting numbers with the 0 added into the set. Great, now we can solve the type of problem that we had before. But can you come up with a problem that we can't solve? In other words, a problem that you can make using only whole numbers, but has no solution. The answer is, of course you can. There's a lot of them, but one of them is something like x plus 3 is equal to 0. And again, we know what the solution to this is. We know how to get there. We subtract 3 from both sides. This is just a simple basic linear equation. And 0 minus 3 equals, oh no, if the only numbers you know start with 0, this has no solution. And you may recall that when you were in elementary school, you didn't know about negative numbers the same time you knew about counting numbers and whole numbers. So if you were doing a subtraction problem like 5 minus 2, you said it was 3. But if you said 2 minus 5, sorry, no solution until you learned about negative numbers. So we fixed that problem. And guess how we fixed it? Well, by throwing in the types of numbers that we don't have. And again, historically speaking, it was controversial whether or not the concept of a negative number was even worth discussing. This day and age, it's just like, oh yeah, those are the numbers that are less than 0. All right, so the story went on for a while, and of course we can make problems using integers that have integer solutions, but not all of them. For example, we could solve 2x is equal to 8 by dividing both sides by 2 and getting x equals 4. But can you think of a multiplication problem that you can set up with integers that does not have an integer solution? Sure, there's lots of them. For example, we can't solve 3x is equal to 1. Well, if we don't know anything but integers, because, well, if we were to do the move, which is divide by 3, what is 1 divided by 3? Well, if the only numbers you know are the integers, this has no solution. So we need more numbers. You see what's going on here. We make up a problem that has no solution. We throw in the types of numbers that fix it, and then we can create another problem that still has no solution. So what types of numbers do we need? Well, you know the solution is 1/3, or as a decimal, you might know it's 0.3 repeating, but that brings us to the set of rational numbers. Now, at this point, we have to stop listing them because they are so densely packed, it's impossible to list them from least to greatest in order. That would be least to greatest, and have every one of them. Try it sometime, but rational numbers, and I should say fractions, are dense in the sense that if you take any two fractions, for example, if I take two fractions that are next to each other, like, or what you think would be next to each other, like 1/3 and 1/2, and there's no fraction in between, well, guess what? If I turn all these into 12ths by multiplying the first fraction on both sides by 4 and the second fraction on both sides by 6, asking for a fraction between 1/3 and 1/2 is the same as asking for a fraction between 4/12 and 6/12, like 5/12. And this will work with any two fractions, no matter how close they are. They're so densely packed between any two fractions, like 1/3 and 1/2, you can find an infinite number of fractions. So it's impossible to list them all. So we have to describe them. Rational numbers is the set of ratios of all integers. And when I say ratio, I just mean fractions. Now there is a restriction. You can't have 0 on the bottom. Something like 5/0 would be bad. Something like 5/30 would be okay. So there is a stricter definition of rational numbers, but let's just say that the rational numbers are what we get when we make all of our fractions. Now you can also view them as decimals because all fractions, all ratios of integers as decimals do one of two things. If it's something like 3/4, you get 0.75. It's a decimal that ends. Or if you have something like, we'll say 5/6, you may not know what that decimal equivalent is, but it's 0.833333, worst 3 ever. But because the 3 repeats, we could just write it once, put a bar over it. So as a decimal, it repeats. All ratios of integers, all fractions of one whole number over another, maybe a negative thrown in there, as a decimal are well behaved, meaning that they end or they repeat. And for the longest time, this was it. We're done. But, you know, mathematicians being the ones they are, like to push the boundaries. What about x² = 1? Whoa, we can solve that. That's not what that's supposed to be. 1 second. That's better. What about x² = 2? x² = 1 has a solution. I know a number I can square and get 1. It was in my first list of numbers, 1. There's another number you can square and get 1, -1, whichever way it's turned on your view. So yeah, x² = 1 we can solve. But what about x² = 2? Well, it's not as easy to see, but there is no fraction that you can square and get exactly 2. There are fractions that you can square and get something close to 2. For example, if I had 707 divided by 500. And if you're wondering where I got that fraction from, ask me outside of class. And squared it, then you would get, let's see, what is 707 times itself? A problem I should be able to do without a calculator. 499,849. And if we square 500, we get 250,000. And if we divide that, I'm not going to write the decimal, I'll just read it to you. We get 1.999396. So it's close to 2, but it's not exactly 2. So what fraction can you square and get exactly 2? And more specifically, what ratio of integers can you square and get exactly 2? The answer is there isn't one. I can prove it to you, but I'm not going to do it within the confines of this video. If you want to see a proof, let me know and I'll throw something together just for you. And for the longest time, there were some mathematicians that contended you can't have a number that does this. Now, we haven't quite gotten to this technique yet, but some of you may be familiar with this. To get rid of a square, you can square root both sides. And if you don't know what's going on, don't worry, it's going to show up later. We do know the answer to this is the square root of 2 or the negative square root of 2. But there were mathematicians back in the day, and this wasn't that long ago, maybe just a few hundred years ago, that insisted that this could not be anything but one of these. In other words, a decimal that ends or a decimal that repeats until it was proven otherwise. To suggest otherwise, that it's a decimal that neither ends nor repeats, kind of spat in the face of everything they built their foundation on. And in one case was actually resulted in somebody's execution. I kid you not. So yeah, it was a little contentious back in the day. But my point is we made an equation using rational numbers. 2 is a rational number. It's 2 over 1. Every integer like 2 can be thought of as a ratio. So we're adding more numbers to the set that we already had, but none of those will solve this. So now what? Well, we need more numbers. So we bring in the real numbers, which are all possible decimals. Now you might be thinking that's what we said up there. I said, no, that's well-behaved decimals, decimals that either end or repeat, because there are some decimals that do neither. The square root of 2, for example, if you put it in a calculator, it will show you so many decimals, but it's only showing you so many because that's all it can show you, as it actually goes forever and never repeats. Pi is another example of a real number whose decimal goes forever and never repeats. So we're going to throw in all of the misbehaving decimals, the ones that neither end nor repeat. Those are called irrational numbers. And we get something called the real numbers. And see if I can there we go, make my name go away. But the real numbers are all possible decimals. So it's the rational numbers that we already have, the fractions, which are well-behaved decimals. And then we bring in all the other decimals to fill in the little gaps in between. And everything went good for a while until somebody tried to break things, and this is what they asked. We can't solve x squared equals -1. Now, this one might be a little easier to see because you know that if you multiply positive times positive, it's positive. Negative times negative is also positive. The real numbers, as you probably know, all live on something that's usually called the real number line, which usually has 0 in the middle, but truth be known, any number can be in the middle you want. Nobody said when you look at a number line, you must stare right at 0. You can look at any number that you want, but you know that the positive numbers are over here. You know that the negative numbers are over here. That says positive and negative, believe it or not. And what happens when you square one of these things? Well, if you take a positive number and multiply it by itself, positive times positive is positive. So we can't get -1. If you take a negative number and multiply by itself, negative times negative is positive. So we can't get -1 when we square a negative. And the only number left is 0, but 0 squared is 0. We're still not getting -1. So this seemed to be the end of the road because, well, we can't square a real number and get -1. And that was it. Math is over. Until, just like before, somebody said, what if? Now, the problem with what happens next is that it seems like we've exhausted all of our numbers. The whole number line is now accounted for, including all the really misbehaved decimals across it. And so finally somebody said, well, maybe we're just not looking in the right place. Maybe the answer to this does not live on the real number line and therefore is not real. Well, There was supposed to be a square up there. Give me 1 second to type it. I forgot something here. If x squared equals -1 has a solution, it can't be a real number. So either math is over or we just need more numbers. So what was the resolution? The resolution is, all right, we're going to kind of do the same thing we do in algebra when we don't know the answer to something. We're just going to let something represent that answer without knowing what it actually is. So somebody said, all right, we are going to just represent the solution with something without knowing what it equals. And we need something, we'll use a letter because that's what we do in algebra. But I need a letter to say that this number is not real. When I say real, I don't mean as in it exists, you can touch it and everything. I mean real as in, living on the real number line. So what's a good word meaning not real? Well, imaginary. So let's, for lack of a better word, make up a solution and call it I, lowercase I. And that I is for imaginary, meaning the opposite of real. Again, real in this case means on the real number line. So the solution, wherever it is not on that number line. So it's off of it somewhere. Where could it possibly be? Now, if we just accept for a moment that we're going to make a solution to this and call it I, if this is a solution to this, then I should be able to substitute it and make the equation true. I squared is equal to -1. And people look at that and go, no, you square something, it always comes out positive or 0 if you square 0. But that's if you limit your thinking to what is on that one number line. There may be some numbers off of it. In fact, I'll show you where the I lives in just a minute, that when you square them, you get -1. All right, so let's just run with this and see what happens. There was a lot of contention over why are you doing this? This doesn't make sense. What does this represent? What is it useful for? What application does it have? But that was the applied mathematician speaking. The theoretical mathematicians were like, really don't care. We're just solving the problem for the sake of solving the problem. If it's good for something, y'all worry about that. We're just going to do math for the sake of doing math. And I'll be honest with you, a lot of math is discovered by doing it for the sake of doing it and not doing it to try to solve a real world problem. Now, a lot of that type of math eventually has a real world application. It's just that at the time, the people that came up with it were way ahead of their time. All right, so time to make a definition. Definition, the imaginary unit at I, and that's the phrase that we're defining. We're using the word unit to mean one, as in the number one I. The imaginary unit I is the imaginary number whose square is -1. So if you ask me, why does I squared equal -1? I will simply say, because that's its definition. It's defined to be the number that does that. Now, this doesn't set well with some people because some people want to know, that's cute, I know what I does, but what does I equal? Well, if you treat this like an equation and try to solve it, you'll never solve for I, it's a definition. But if you tried to solve it, you would square root both sides to cancel the square. And if you square rooted both sides like that, the square on the left would cancel, leaving you with just an I. And on the right, we would have a square root of -1. And if you're thinking, I can't do the square root of -1, you're thinking linearly on the real number line. You're right. As a real number, the square root of -1 is not real, but it could be imaginary. Excuse me. So we're going to say that the imaginary unit I is defined to be the answer to the square root of -1, which is kind of equivalent to saying that it is defined to be the solution to x squared equals -1. Now, this may be making you go, what have I gotten myself into? But here's what you need to know at this juncture. There are two ways to view what you are seeing here, not in terms of symbols, numbers, equations, exponents, and all that jazz, but in terms of words and what you are going to be expected to do. And these are actually pretty easy. Two ways to view this. Way number one, if we look at the equation on the left that says I squared equals -1, you can view that as the following set of instructions. If you see I squared, change it to -1. You can ask why, and I will say because that's what I does by definition. So don't think of it as I got to solve what I squared is. Excuse me. I hate these weather changes. No, I can't. I got to solve I. I got to figure out what I equals. I don't know what I equals. I'm not asking you to know what I equals. I'm asking you to know that when you square it, you get -1. If you see I squared, change it to -1. That's one of two things that this is telling you. The other thing is kind of the other equation, and we're going to run across this one also. If you see the square root of -1, which you normally don't see, but you're about to encounter, then according to this equation over here, it's equal to I, so we can change it to I. So if you remember anything, it should be these two sentences here. If you see I squared, change it to -1. If you see the square root of -1, change it to I. Again, you don't have to know exactly what I is, where it came from, its history, and all that jazz. You just have to know if you see I squared, change it to -1, we will. And if you see the square root of -1, change it to I. Keep that in mind as we go through this series of videos. All right, just a few definitions to get out of the way now. We've defined an imaginary unit, but now we're going to define what's called an imaginary number. The imaginary unit I is a building block. An imaginary number is any number of the form b times I. I know that looks like the prefix by, or the word by, if you think of it as a word, but it's actually b times I, where b is any real number and I is the imaginary unit. In other words, an imaginary number is a number that has an I on it. So what's an imaginary number? Well, I just said it's any number that has an I on it. So for example, let's take this back up to 2436 point font. For example, 3i is an imaginary number, singular. We'll copy this because I'm going to be writing it a lot. Whoa. 1 second, folks. Copy. Now let's widen this text box. It's real easy to spot an imaginary number. It's got an I on it. -5i is an imaginary number. Let's see, 7.2i is an imaginary number. Any number that has an I on it. Now, if you're wondering why I put all those spaces, it's because I'm going to draw the next one because I can't type it. 3/2 I is an imaginary number. Let's do one more. And again, it doesn't matter how pretty or ugly the real number is. You could say the square root of 2 times I is an imaginary number. Now, I will admit that when you have a square root and an I multiplied together, it's usually better to put the I in front. It's one of the rare cases you put it in front, because if you put it afterwards, you might think it's inside the square root when it's not. But that's all an imaginary number is. Any number of the form b times I, a real number with an I stuck on it. That's all an imaginary number is. Now, I mentioned that none of these numbers live on the number line, the real number line. I'm just going to briefly show you where they do live. This is not something you're going to be held accountable for. It's just an FYI. Might give you a minor heart attack, but I promise you we're not going to explore this concept. I'm simply showing you where this number lives. Here's 0. If I go 1 to the left, I get 1. 2 to the right is 2. 3 to the right is 3. But if I go to the left, I get -1, -2, and -3. So the I does not live on that. Those are the real numbers. Those are the real numbers. These are the real numbers. I is not real. It is an imaginary number. So where does it live? Well, prepare to have your world slightly rocked. Here's where the number I lives relative to the real number line. It does not live one space to the right. It does not live one space to the left. It actually lives one space above. I kid you not. The imaginary unit I lives one space above the number 0. In fact, what you and most people don't know, because they never needed to, is there's a whole other number line that drops right through 0, except every number on it has an I. So for example, going up 1, you get 1i, or just I for short. Going up 2, you get 2i. Going up 3, you get 3i. Going down, you get -I, -2i, -3i. And if you're worried about, oh my gosh, we're going to do graphing with imaginary numbers. No, we're not. Is it a thing? Yes, it is. Is it in this class? No, it's not. Does it have usefulness in the real world? Actually, yes, it does. Way beyond the scope of this course. I was just showing you that the imaginary numbers have a place to live. They actually live, and I meant to make that other number line a different color. We'll make it, I don't know, what's a good imaginary color? I don't even know what that means. We'll just say pink. I don't know. I just chose pink for, wait, that's supposed to have two arrowheads. I'm having way too much fun. All right. So yeah, the imaginary numbers actually live on a vertical number line that drops right through 0 on the real axis. And the reason it goes through 0 is because from an imaginary perspective, that was not supposed to be that. From an imaginary perspective, where they, come on, where they cross is 0i, but 0 times anything is 0. 0 is the only number that is both simultaneously real and imaginary, because 0 times anything is 0. But I want to remind you, I'm not going to hold you accountable for that vertical number line with the eyes on it. I was simply letting you know where the imaginary numbers live. Just a little more and we'll be done with this video. When you pick up a new type of number, like imaginary numbers, the previous types of numbers still exist, which in this case are real numbers, all the numbers you've ever seen. And it's a natural question to ask, what happens when we try to combine the two? So in this case, what happens when we try to add real numbers with imaginary numbers? For example, let's say I ask you to add 3 and 4i. So what do you think you would get? I'll give you a hint. If this question had any other letter, we probably wouldn't have to discuss it nearly as much. For example, what if I asked you to add 3 and 4x? Now, if you said 7x, you need to take a step back and remember the rule for adding like terms. Like terms have the same letters with the same powers. These are not like terms, they cannot be added. If it said 3x and 4x, they would be like terms and you would get 7x. Because the x is the object and you have 3 of them and 4 of them, you just have 7 of that object. The object doesn't change. 3x plus 4x is 7x. But without the x on the 3x and just a plain old 3, the answer would be it's a trick question because these are not like terms. But if I said, but I want you to write an answer, well, you could just say, okay, 3 plus 4x is the answer. That's the best I can do. Since they're not like terms, all I can do is stick the plus between them, look at it and go, well, wish I could add them. Can't because they're not like terms. So what does that mean in terms of up here? Well, the exact same thing. They're not like terms in the sense that one has an I and one doesn't. So the best thing you can do is write 3 plus 4i, stick a fork in it and say, that is my answer. I can't combine them. They're not like terms. One's real, one's imaginary. One has an I, one doesn't. So I'm stuck with the attempt to add them. It's a failed attempt at adding something. 3 plus 4i is precisely that. It's 3 plus 4i. Cannot do anything else with it. However, we're in a slight dilemma. What do we call this thing? Can we call it a real number? Well, no, part of it is not. Part of it is imaginary. Can we call it an imaginary number? You could, but I wouldn't because part of it isn't. There are some people that will call this an imaginary number because it has an I in it, but really half of it, the 3 is not imaginary, it's real, and the other half of it is not real, it's imaginary, 4i, it's got the I. So what do we call this failed effort to add a real and imaginary? Seems like we're back in the same development of math. We've run into a problem that doesn't have an answer. So either A, we need a bigger set of numbers, or B, we at least need to give this some other name besides real or imaginary. And that's where the word complex comes into play. A complex number is any number of the form A plus BI, where A and B are real numbers and I is the imaginary unit. It's a failed attempt to combine a real number and an imaginary number. Now be careful. The definition makes it look like that the A and B are positive, but the A and B can actually be any real numbers, which includes the possibility that they could be negative. So don't get lulled into the sense that, oh, they must be positive numbers because they look positive. They might be negative numbers. So for example, 3 plus 4i is a complex number. I'm going to highlight the phrase is a complex number because I'm going to be writing it a lot. 4 minus 7i. I don't think I need those spaces. 4 minus 7i is a complex number. As long as you got a part without an I and a part with an I, it's a complex number. What about something like 5? Is that a complex number? No, you said it has two parts, real part and imaginary part, but believe it or not, 5 is considered to be a complex number for two reasons. Number one, backing all the way to the beginning, in this development of numbers, we didn't step to the side, we just added to what we already had. So when we went from real numbers, all possible decimals, up to complex numbers, then our complex numbers should include what we already started with. But how can I justify that 5 is a complex number when it doesn't have an imaginary part? The reason it's considered a complex number is because 5 is equal to 5 plus 0i. Let that sink in. Normally, I can't figure out what a number times I is unless that number is 0. 0 times I is 0. 5 plus 0 is 5. So when you have a real number without an I, you can't call it an imaginary number, but you can call it a complex number because its imaginary part is 0. Its imaginary part is 0. Imaginary part is 0. And by the way, that is the correct term for that part of the number. The part with the I is called the imaginary part. The part without the I is called the real part. And I think I'm going to go back up here in this definition and sneak that in. The A is called the real part, and the BI, that's supposed to be in quotes, BI is called the imaginary part. Now, there are some books will say that the imaginary part is just B. There are some that say it would be B with the I on it. So, for example, in the ones that we've seen so far, the examples that we've seen so far, 3 is the real part, 4i is the imaginary part, although some people will say it's just the 4. 4 is the real part, negative 7i is the imaginary part, 5 is the real part, 0i is the imaginary part. So what you can glean from this is all real numbers are also complex. I'm trying to get this text box here. All real numbers are also complex, colon, their imaginary part is 0. Let me see if this will all fit on one line. It will not. So I'll take out the word also. All real numbers are complex, their imaginary part is 0. Okay. Oh, one more example, but I need to make some room. So I'm going to grab all this and try to move it up. See, I grabbed everything successfully. Yay me. All right. So one more example of a complex number. Negative 3i is a complex number. Now you might be thinking, I thought it has to have a real part and imaginary part, but do you remember what happened on the last one? The imaginary part was 0. Negative 3i is equal to 0 minus 3i, because 0 minus anything is just, well, 0 minus 3i is negative 3i. So that means that its real part is 0. So what this tells you is pretty much the same thing that we just said there about all real numbers are complex, their imaginary part is 0, but now we can say all imaginary numbers are complex. And I don't know if I'm going to be able to fit it all in there, so I'm going to take it down a font size, turn it red, and change the word real to imaginary so that it all fits on one line. All imaginary numbers are complex, their imaginary part is 0. I think I'm going to go back to this text box and take the font size down too. Come on, come on, come on. There we go. But I want it red, please. Thank you. So all real numbers are complex, their imaginary part is 0. All imaginary numbers are complex, their real part is 0. It's like something else needed to be changed. Their real part is 0. Okay, so what's left? Oh yeah, the definition of what's called a conjugate. Now this will come up later in the last video in the series. The conjugate of a complex number is the complex number with the same real part, but the opposite imaginary part. This is much easier than it sounds. For example, if I asked you, what is the conjugate? And the word conjugate here is a noun, not a verb. It's not a Spanish class where you conjugate a verb. What is the conjugate of, let's just say 3 plus 4i? We've been using that quite a bit. Well, the conjugate of a complex number has the same real part, but the opposite imaginary part. The real part of this is 3, so we keep it. The imaginary part is positive 4i. The opposite of that is negative 4i. The conjugate of 3 plus 4i is 3 minus 4i. Question, what is the conjugate of negative 7 minus 5i? Think about it. Same real part, opposite imaginary part. So it starts with negative 7, but we change it from negative 5i to positive 5i. Okay, let's do a couple more that are trickier. What is the conjugate of 2i? Now, if you're thinking that's not an imaginary number, a complex number, remember, every number is a complex number. If it's missing something, it's because it's a 0. Now, we can think of 2i as 0 plus 2i. Its conjugate is 0 minus 2i, or just negative 2i. So I kept the real part and I took the opposite of the imaginary part. Now, if you were just thinking 2i because you knew to take the opposite of the imaginary part and that's all it had, great. But I'm going to put this back in. Oh, man. Hold on. Copy and paste is an abomination sometimes here. We'll just say since 2i equals 0 plus 2i, its conjugate is, there we go. All right, I do want to show one more. I'm not sure if I have room on this. I'm going to take the font size down just for a second. Why did it go back to red? I didn't tell it red. And try to sneak one more in here. Then I'll blow it back up, see if I can make it fit. What is the conjugate of 7? It's not a complex number, it's real. All numbers are complex. If it's missing a part, it's because it's imaginary. So using the same argument, since 7 is equal to 7 plus 0i, since 7 is equal to 7 plus 0i, then its conjugate is 7 minus 0i, but it still has no imaginary part, so it's just 7. I'm going to go back up here and write 0 minus 2i, or just negative 2i. Let's see if this will fit if I put it in 36. No, but maybe I can move everything up. Let me see if I can move everything up real quick. Move it on up. And if you're wondering why is it so difficult to do this, it's because there are tools that are in my way that you can't see, that I use to change colors and stuff like that, and they kind of get in the way. All right, so that looks good. And that also wraps up this video. So if you have any questions, let me know. Oh, by the way, the whiteboard PDF for this will have one more page, because this page where I drew this picture was not something I planned on doing. So if you're wondering why you're looking at the notes and at the end it has this picture, that would be the reason why. All righty.